In this video, we'll begin our discussion of section 13.3. This is about the derivative of a multivariable function. Let's just first talk about the derivative given just a function with one variable. Typically, this was the slope of the tangent line, right? So what does the derivative of the multivariable function look like if we're talking about a surface in R3? Is the slope of the tangent line of the surface at a point, is it the slope? Well, the thing is about this is when we talk about a tangent on a surface, we actually have, and if we think about it, okay, take a surface, let's look at the surface down here. We have a green surface there, and notice we have that orange line moving, that's tangent. I also, on the right, have a tangent line moving left and right. If you think about it, we can also put a surface, another thing there, another thing there, another thing there. All these being tangent, right? Because they would just touch that surface at that one point. I think I have a picture pulled up. Sorry for the other stuff here. It's a tangent plane, but you can capture the idea here that we can put an infinite number of lines through that point P that stays in the plane there. So the problem here, and when we ask ourselves, is it the slope of the tangent line of the surface at a point? We don't know, right? It could be, it's too ambiguous. So, and the reason being is because we have an infinite number of tangents, right? We can fit on that plane, that picture I showed you, all those tangents will fit on there in any direction. We could just turn the tangent line any way we want. Let's go back to that picture real quick. I could have a line going through P on the direction of those two lines that are on there, staying in the tangent plane, staying flat. I could turn it any direction I want and get some kind of tangent line that touches that point. So the answer is there are an infinite number of tangent lines. So we have to focus on a direction. So to find the slope of a tangent line to a surface at a point, so if we're talking about 3 dimensions, we must give the tangent line a direction. If we don't figure out a direction, the derivative doesn't really make sense when we think about it in just the x direction all the time, and then making sense for everything, or in the y direction all the time. What we have to do is consider every single direction that tangent line could be pointing. So to start off, let's talk about tangent lines in the x direction and in the y direction. So the green here is our surface. This orange line that's there is parallel with the x-axis, or skew, really. They don't run in the same direction, but they are skew. They'll never run into each other. Another way you could put it is that orange line is contained in a plane right there, right? This blue is a plane, and that plane, the blue plane, is parallel to the xz plane. So the way I think about it too is, if we turn the graph sideways and look at it like this, right? Imagine turning it where that's what we see, right? And then we'd have that orange line going through right here. Take a minute, think about turning that picture. The y is coming out at us now, z going straight up and x going to the left and right. That's the way that orange line would look. Let's go ahead and throw it, put it in orange here. That is that orange line. So it actually describes how much does z change when x changes. The same thing here, that's in the x direction, right? It's describing how much does z change in the x. Well, we could also do the y direction. These are going to be the two main directions that we'll focus on, even though later we will talk about a derivative that is fully directional, any direction we want. So for this section, we'll focus on the tangent lines that run in the direction of the x-axis and the ones that run in the y, right? These are called partial derivatives. What is happening is, let's consider that xz1, this one again. Think about the y through that whole line, that orange line, the y value, and the blue plane. The y value is held constant. So if we hold it constant, then we can get a derivative that describes z, or a function, right, or f, or however you want to say that, z or f. We could describe how that function changes when x changes. But if I go to this picture on the right, this describes how z changes when y changes. Notice we could also push this on the z, y plane, and we'd have something like that. It describes how much is the z changing when we change y. Okay, these are called, and some of you guys probably have been working with these in some of your engineering classes, but these are partial derivatives. What we do, and we'll get plenty of practice. I'm going to run you guys through so many examples for this. So let's talk about notation. For a partial derivative, what we use is that squiggly D looking thing. I used to think it was a Greek letter. Found out recently it's not a Greek letter. It's just a letter, a symbol we use for partial. So what this means is hold. So I'm going to write this out. Holds y constant. It gives the slope, sorry about that, of tangent line to the surface at a point in x direction with respect to x. That's what that means, with respect to x. So it holds the y constant, just like our picture up here on the left. That blue plane holds the y constant. Y is not moving left or right. And then it lets us just examine x and z. Okay, for this one, it's doing a different color, so it's not stacking on each other. All right, so this holds x constant, gives slope of tangent line to the surface at a point in y direction with respect to y. So similar, right? One's with x, one's with y. It just holds the other variable constant. Let's talk about some of the notation that's going to be used throughout this, and then we'll start getting our examples underway. These are actually easier than they seem. I know when I've taught this before, my students are always like, I feel like you have totally wrecked my understanding of derivatives, like fighting against the habits that they have built through their Calc 1 and 2 process. So let's get some notation under our belt. This first thing is how we are used to seeing it. Sorry for the scrolling there. We're used to seeing it this way, with the partial of f with respect to x, or the partial of z. This is the shorthand. I like this notation, using the x there, or using the z there. And then the same thing with y, right? We can do a bunch of other variables as well. We will do that through this section. All right, let's get some practice. This is going to feel weird until you get used to it. So the partial of f with respect to x. I treat y like it's a number. You can pick any number you want, plug it in if you want. Go through and plug in 1 for the y's or something like that, and that'll help you. So looking here, I'm taking derivative with respect to x, and I treat the y like a constant. So I get 6x to the first, and I leave the y third alone. That's it. Here, with the x, I do 2x, and I leave the y attached. 4x squared becomes 8x. Minus 2y squared, that's all y. That's a constant. It's not x. So the derivative of a constant is 0, and the 1 is 0 too. That's how we take a partial. You literally treat y like a constant. So now I do the partial of f with respect to y, and I get 9x squared y to the second minus x squared. That one's a little weird. Think about it. If that was x is a constant, so if it was a constant times y and I took the derivative, I would just get the constant. The 4x squared is all x. That's counted as a constant. It's gone. Then I get minus 4y. And that is my partial of f with respect to y. That's it. It does take some practice. We're going to do a bunch in here. You're going to do a bunch in your homework. And hopefully we can get this down. Right, so we have, and let's make sure you understand what this is. This is the how f changes with respect to x. The other one is how f changes with respect to y. These aren't together. We are going to talk about what they're going to look like if we put them together here in a moment. All right, so we have this function, and we're going to take each partial. So I have the partial with respect to x. So cosine of y is considered a constant. So the derivative of e to the x is e to the x, no product rule, right? You're going to want to do that. That's where you're going to mess up, and you're going to be frustrated because you did a whole product rule when you could have just not. Okay, then this one, e to the y is a constant, so I just leave it. Derivative of sine is cosine. There is my partial with respect to x. Right, we got to do our partial with respect to y. We get negative e to the x sine of y. Derivative of cosine is a sine. E to the x is a constant. I don't touch it. And then y here, I get e to the y, but sine of x is a constant. So just like if it was a 7, I would leave it there. So there are my partials. All right, let's take a function here. This is going to be helping us determine when we need to use the product rule and not. All right, we're going to do the partial of that z function with respect to x. Notice there's only one x. So I keep the y because that's considered a constant. And then I get ex to the y third, because e to the something, the derivative of e to the something is e to the something. Then it's the chain rule of the inside. So the derivative of x y cubed, be careful, y cubed is considered a constant, so we just get y cubed. So that means this is y to the fourth e x y cubed. All right, let's do y. Y is going to be a bit more complicated. Y now, we have to have a product rule. Derivative of y is 1, ex y to the third. Plus I leave my y there. I take the derivative of e to the something is e to the something times the chain rule. Now that 3 actually does come down because I'm doing it with respect to y. So this is equal to ex y to the third. I can actually factor that out. And I'm going to have 3x y to the third. You could have left it, just multiplied out that first line to get the second line, and you could have stopped there. That would be perfectly fine. All right, let's start letting these get a bit fun here. You're going to have a table for this, but just in case, we just need to know when to take them and when to not. Partial of f with respect to x. All right, the only x is that top one. That is my variable. This calls for a exponential log, so we get the ln of y times y to the x. That's the rule for like 3 to the x or 2 to the x. Y is a constant now, so I treat it like a constant. I also have the partial of f with respect to y, and I treat that's a power rule. X is constant now, so the constant comes down, and then I subtract the power by 1. Nothing new. You're just treating that other variable like a constant. This next example, we have a cosh. You would use a table. All right. We call this z in this one. Zx. Right? And so x, it's a product rule, so I got 2x cosh. It's just a hyperbolic cosine. Plus, I leave the x squared, and I take the derivative of cosh, which is sinh. And it's x over y times it's with respect to x, so the chain rule would call for 1 over y. X over y. Derivative of x over y is 1 over y. X is constant. X is the variable this time, so it would be like this, like 1/3 x. The derivative of this is 1/3. So if I have 1 yx, the derivative of that is 1y, following that same pattern. Now I do with respect to y, it's not a product rule because I only have 1 y, so I get hyperbolic sine of the same argument, and then times its x. The x was going to stay, so this becomes negative x over y squared. That's the derivative of like 3 over y. All right, run through that and see how that works, and you'll see the pattern here. So there are our 2 answers. Just so you know, you need to be able to differentiate, tell the difference between when to use the product rule and when to not use the product rule. All right, I have a few more. We can apply this when we have multiple. I can do each variable here. I have that w. Notice that it's x, y, and z. So I can do each partial. I have w in the partial with respect to x, which is 6x squared plus 3y. And then this doesn't have an x, so it's 0, doesn't have an x, 0. I can also do w with respect to y. This first term goes away because there's no y. 3xy becomes 3x, and then 2yz. If I'm doing it with respect to y, I get 2z. Minus z squared is a constant when compared to y, so it's gone. The next thing we can do is wz, Well, first term is a constant, second term is a constant, there's no z. This has a z, so we get 2y minus 2z to the first. Sorry about that. So there are partials. What they mean in this case is, how does w change with respect to x? That would give us our slope at a point of the tangent line running in the direction of x, the direction of x-axis, parallel with the xz plane. All right, we have this one here, and this will be our last one for this video. We have 4 variables now. That's perfectly fine. We can find f partial of x. Notice there's only one x, so this would be like everything else is constant. So if it was like a 3x, the derivative of this is 3. So if it's everything else x, the derivative of this is going to be w squared over y sine zw. That's it. That is with respect to x, because all those are considered a constant. It follows the same pattern. They also want us to do f with respect to w. So the w, we're going to have to do a quotient rule. So low d high with respect to w, so we get 2xw minus high, so xw squared, d low with respect to w, y is gone, sine becomes a cosine, zw, and then I chain rule that, I got to multiply by a z because it was with respect to w. All of that over y plus sine zw squared. We could clean it up. It's not going to get much better. I got 2xw y plus sine of zw, and I could maybe mush all this stuff together, w squared z cosine zw. Right, okay, and we get an x in there too. I forgot that there. Sorry, that was out of my notes, so that's what I was considering there. So there we go. That's the best we're going to get. Please fight every urge to do that. Please do not cancel those. You can't. They have to be in all 3 terms. So that's how you take a partial derivative, get some practice under your belt, do a bunch, because you're going to be breaking a habit that you've already have formed. So there we go.